we present a pipeline for the creation of digital doubles from real objects. This includes the geometry of the object, but also the color called albedo. Unlike photographs, albedo is unaffected by changes in lighting and is free of shadows or shading artifacts. It is the true color of the object and solely determined by material properties. Our method combines two approaches. Photometric stereo uses images under different light conditions and is the method of choice for capturing delicate surface details as well as albedo and normals. It only provides relative depth information and it is very sensitive to discontinuities. Depth from stereo uses camera pairs to determine absolute depth values. It is robust towards discontinuities, but exhibits less surface details and does not provide albedo. Only few methods combining both approaches to counteract the respective shortcomings have been suggested so far. These methods either use photometric stereo as a second stage to enhance already existing depth maps and 3D models, or use photometric stereo to replace the smoothness term in depth from stereo, but neglect the effects of discontinuities. Our approach integrates photometric stereo and depth from stereo at a deeper level. By identifying depth discontinuities at an early stage through a shadow-based segmentation, we can use photometric stereo for the shape of each segment. The correspondence search in depth from stereo can then be performed on a segment by segment instead of a pixel by pixel level. Our algorithm uses a calibrated stereo camera pair, in conjunction with multiple known light sources. In each image, only a single light source is active. Even for simple geometries, self-shadowing might be inevitable, and robust photometric stereo requires distinguishing illuminated from shaded pixels. Since depth discontinuities tend to cast shadows on more distant parts of the geometry, we use shadow boundaries to build a discontinuity-sensitive image segmentation. The shape of each segment is determined by photometric stereo, and the segments are positioned at a random depth within the capturing volume. Next, we iteratively refine depth and fuse adjacent segments into larger meta-segments where appropriate. In each step, we pick one meta-segment together with its wandering neighborhood. Under the assumption that this region represents a continuous surface, we use photometric stereo to generate a candidate depth map for the region. The candidate depth map is evaluated for each segment by projecting it into the secondary view and comparing image intensity, but also normal maps and shadow masks. Furthermore, we consider integration errors within the segment and between segment boundaries. Using Boolean optimization, we find the optimal decision between candidate and current depth map for each segment. Those segments adopting the candidate are fused into a meta segment, and the depth maps are updated. In the next step, we can use this new meta segmentation to pick another meta segment, expand it, and adopt or reject a new candidate depth. Here we can see the algorithm in action. There are typically 10 to 100 times less segments than pixels in an image, and fusing meta segments gives another factor of 10 to 300. Most of this reduction takes place during the first few iterations. For a quantitative evaluation, we use the medical wax model of a human nose. This is a challenging object due to the wrinkles and microstructure in the cloth and the depth discontinuities around the nostrils, none of which have a negative effect on reconstruction quality. The tip and the bridge of the nose demonstrate that we can also handle specular materials, albeit with some effect on reconstruction quality. We also performed a qualitative evaluation using a succulent plant and an artichoke. In lack of ground truth data, we use our reconstructed model to render the objects from a novel view and compared the results to images which were taken by a third camera. Finally, we used synthetic datasets with Lambertian surfaces to compare to previous work. The first two datasets were generated from pore deep face scans of a male and a female head. We compare our method to photogeometric scene flow, a combination of photometric stereo and depth from stereo designed specifically for facial reconstruction, as well as to HitNet, a state-of-the-art depth from stereo algorithm. Our method achieves comparable results to PGSF with improvements in discontinuous areas. The same is true for the female head. We outperform HitNet in both cases. As a geometrically more challenging example, we used an origami-inspired scene where our method has substantially fewer smearing artifacts than both other methods. We believe the reconstruction quality, together with the iterative reduction of meta-segments, demonstrates the full potential of integrating photometric stereo with depths from stereo. In the future, we would like to investigate how our pipeline translates to a multi-view setup.